pretty standard problem. You can expect one like this on the test where some kind of a wheel is spinning, might be on a car, might be on a bike. You got to figure out how fast the object is moving. Linear speed. So, V equals the radius times omega. What do we know? What do we don't know? We know the radius. All right. The radius is 26 inches.
It's 13 inches. 13.
Oh, that's diameter. You're right. 13. Now, omega. You got to be careful about omega. Omega is an angular speed. It's not how fast something is moving. It's how many rotations it's having. Revolutions per minute is not an angular speed. An angular speed is in radians per unit of time, not revolutions per unit of time. So we have 125 revolutions per minute. Now where does that come from? This is a lot just like dimensional analysis. We've got to change this instead of revolutions per minute into radians per minute. Okay, so we've got to cancel this revolution unit of measure. So 2 pi radians is equal to 1 revolution. So we put revolution on the bottom of this conversion factor so it can cancel out that revolution unit of measure. So you're absolutely right. It's 250 pi radians per minute. That we can now call omega because it's in terms of radians per unit of time. It doesn't have to be per minute. It could be per second or per hour, but it just has to be radians per something unit of time. So we have everything we need. We can now calculate the linear speed. Radius is 13. Omega is 250 pi. Now for the time being, let's just leave pi in there and multiply the numbers. And we'll multiply pi at the very end. Just so we don't have to do a lot around it. So we have 13 times 250. That's 2,250 pi. But now we have a problem. What is this in terms of? Well, the 13 inches supersedes the radian because a radian is actually a linear measurement. A radian measure is just a measure around the outside of a circle, so it's not the same as a degree measurement. So we're actually in terms of inches per minute, which is okay, but the question specifically asks for miles per hour. So the whole rest of this is just doing a bunch of unit analysis, converting inches to feet, feet to miles, and then minutes to hours. That's not too bad. So, what do we do? What's the conversion factors here? We got to go from inches to feet, and then from feet to miles. Let's do that first. 1 foot is 12 inches. Inches have to go on the bottom because we have inches on the top there. And I'm totally blown away that this is not common knowledge. But how many feet are in a mile? 5,280. So where does that one go? I mean, where does the feet go? 5,280 feet go on the bottom. That's 1 So now we've got it into the correct distance. It's in miles, but it's miles per minute. So let's now convert minutes to hours. How do we do that? What's the conversion factor here?
You put 60 minutes.
60 minutes, good. We have to put minutes on the top, so the minutes here cancel. 60 minutes is 1 hour. So, first we had to do 3250 divided by 12. Then we had to divide that by 5,280. Then we have to multiply that by 60. And then finally we can multiply it by pi. Oh, what? She's only going 9.6 miles per hour. That is a slow. Maybe she's going uphill. We can't assume. She's going uphill. It's an 11% grade. Man, that is really slow. She's just going on a nice stroll. It's a Sunday afternoon.
Faster than what you're doing there.
What's that?
Faster than what you're doing there.
You can't go more than 9 miles per hour and drive yourself. 5? So you can't even press, because you could idle at 5 miles per hour, can't you?
Yeah, basically. Yeah.
Is there a teacher in the tower that watches you guys?
Yeah.
Yeah.
Well, I did it in the summer,
Well,
but they didn't
yell at
even
you if
watch,
you
and
get
you could
sick.
just do it over the crowd.
I took driver's ed. Our teacher would sit in there and swear at all of us. What the heck are you doing, you stupid son? You're going to kill everybody. You're the dumbest piece of... You guys are... I'm serious, he was a mean guy.
Maybe you're just being a big Maybe it's because you're
Let's try another one.
that kind of doesn't really make it.
No, but they had... Half of our cars were stick shift. So we had a bunch of kids stalling out all over the
It makes
place. On
sense
the
for your BYU. You said it makes sense for your BYU.
I was saying, why are there 3 legs coming off the cross hollow?
Well, these are the pedals,
Oh,
and this is the seat posting.
okay, those aren't pedals.
Those are pedals.
Those are bigger.
Oh yeah.
Are you just saying that and then we're going to draw it and you're going to be like, you didn't have to draw that?
No, you have to drive.
Okay.
The radius of this rear wheel is 13 inches. The radius of this front sprocket here is 4 inches. And the radius of this little chain wheel back here is 2 inches.
It's that little tiny circle.
This little teeny sprocket, I guess they call it back there. And the cyclist pedals at 40, and that's slow too. These are slow bike rides. 40 RPMs.
Maybe they're really traditional wheels. I was going to say they should have big wheels.
Maybe it's just me and teacher.
Huh. Party.
Maybe it's not a real cycle.
Maybe the cyclists have like that.
Find the angular speed of the 2-inch wheel sprocket. Find the angular speed of the 2-inch sprocket.
What was that time sample?
What's that?
What's that time sample?
Revolutions per minute. Now, I'm sure you all know how bicycle work, but just so we're clear, the pedal turns this chain sprocket right here, right? And it's connected by a chain, and that in turn turns this wheel sprocket. So when the pedals turn, that turns the sprocket. That sprocket's connected to the wheel, so the wheel turns. Question for you. This is turning at 40 revolutions per minute. Does that mean this little teeny wheel is turning more, the same, or less than 40 revolutions per minute? Why more? It's smaller. Less circumference. Okay. It does turn faster. What is the same? There is something that's exactly the same about.
The whole circle.
The distance
Okay.
they move. Something. I don't know. How much did
The distance that they move. Let's stay on that for a second.
Okay.
What's it called when you start measuring around the outer edge of a circle?
Circumference?
The whole entire thing is the circumference.
Oh, they have like the same distance.
Arc length. Okay. Because these two sprockets, the chain one here and the wheel one, because they're connected by a chain, if this turns a certain arc, this one has to turn the same arc, but what's the difference with this smaller one? It has to turn faster in order to move the same arc that the larger one turns. You follow?
Mm-hmm.
This larger sprocket, this chain sprocket, turns a certain arc length. This one has to make that same arc length. Why does it have to turn the same arc length? Because the chain is constant. Okay? The chain keeps them turning the same arc length. The difference is because this is smaller, it has to turn faster to turn the same arc length as the larger one. How do we figure out the angular? Let's go back through some of our formulas. See if we can find one that might work. Are they asking about a linear speed? No. So this one might not be so helpful. They are asking for omega, but we would have to find a linear speed to use this one, so maybe not such a good idea. We have these.
Yeah, there's the angular speed.
Angular speed. We have this linear speed, but that's in terms of s divided by t. What is s, by the way? Arc length. Okay. And then there were a couple on this other page. Hold on. There were a couple before this. We have this one, s equals r times omega. What is this? That's for the arc length.
The radius.
Well, that's theta. So those are some of the formulas that we've learned so far.
Well, we know the radius, so I think we should use that last one.
So we have let's describe what we know. Radius of the chain. Now let's just be clear on the terminology. Which one's the chain sprocket?
Small and what's the bigger one?
This bigger one here, and then the wheel sprocket is the one connected to the wheel. The chain sprocket. What did I say that one was? Where are you? 4 inches. There it is. 4 inches.
I feel like this is a really small one.
A 13-inch radius.
That's only like a foot.
It's a medium-sized button. The radius of the wheel sprocket is 2 inches. All right. Keep throwing ideas around, you guys. Here's the problem with things like this. If you guys can come up with the solutions and we can talk about it, then on a test you'll be familiar with the process of coming up with a solution. If I just show you everything, then on the test I can't show you anything. Yeah.
Since the wheel sprocket is half the size of the chain sprocket, the angular speed will be twice the size of the 4-inch.
Okay, how do we show that mathematically? It is eventually going to be right. You are right, but we need to show that.
So is the RPMs for the chain sprocket?
Yep, because the pedals are connected to this chain sprocket. Let's start with that. If the chain turns 40 revolutions per minute, how many radians is that? 80 pi. So it's going to turn 80 pi radians in 1 minute. That's that's with an apostrophe? Yeah. 80 pi radians per minute. So in 1 minute's time, let's be clear what we just stated here. In 1 minute, this larger chain sprocket has made 80 pi radians.
So the wheel sprocket turns 80 pi radians.
Well, is the wheel sprocket going to turn more or less?
More, because it has twice the amount of change going.
More. It's going to turn more. What's the amount of chain that has run through? If it's turned 80 pi radians in 1 minute's time, what's the amount of chain that's gone through that? What is that going to be comparable to? Something that we've talked about.
If it turns 80 pi radians in 1 minute's time, what's the length of chain that has run through that? I mean, if we were to measure the chain or lay it out flat, what length of chain has turned through that radius?
That would be an arc length, right? Wouldn't that be an arc length? And why are we so focused on an arc length? Whatever arc length the larger wheel turns, that's the same arc length that the smaller wheel turns. Why is it the same arc length? They're connected by that chain, and this is assuming the chain doesn't slip, which it doesn't because it has those little teeth. So whatever arc length this turns, or whatever arc length this measures because of how many turns, the smaller one has the same arc length. It just takes more spins to do that same arc length. So how do we figure out the arc length?
Oh, the arc length is the S equals R times theta. And because we have, 80 pi radius.
So we're basing this off of 1 minute. So if we measure for 1 minute, then that larger wheel has turned 80 pi radius. So that's going to be our theta. What do we use for R? 4 inches. Okay, so 4 inches times 80 pi, that's going to be the arc length in inches. So this is 320 pi. This is S for the chain wheel or chain sprocket. It's 320 pi inches. What do we do with this number now? 320 pi. Now we use S equals radius times theta for the chain, or not the chain wheel, what are we calling this? The wheel sprocket. For wheel sprocket. Now what do we know and what we don't know for
For the wheel sprocket, what do we know? We know the radius,
And we know the arc length.
and now we know s. If we know the radius and we know s, what can we solve for? We can solve for theta.
I think that's supposed to be equal
So R divided by
S equals radius times theta. So we're going to use the same arc length, 320 pi. And what was the radius for that little guy? 2 inches times some unknown radian there. Divide it by 2. And what do we get there? 160 pi. That's the angle, but this is 160 pi per in 1 minute, right? So that we can call that omega now. This is 160 pi radians that it turns in a minute. So omega is 160 pi radians per minute. Question?
Yeah. So they both have, both of the circles, they don't have the same arc length because of the chain.
The chain.
So we could have technically not found, like if we weren't told to find the, what am I trying to say? The find omega for like 4-inch wheel, 4-inch radius wheel. Couldn't we have just done the other one instead? Like S equals 2 times 80 pi radians per minute.
Well, 80 pi radians.
Because that would have gotten us the same answer. Because that's the arc length of both of them.
80 pi radians. Say that one more time.
80 pi radians per minute is the arc length for, I think that's what I was going to say. Or maybe angular speed. That's angular speed for both.
No, the smaller, they don't have the same angular speed.
That's the arc length.
Yeah, but knowing what the next question is going to be, there's a follow-up question to this. This would have been a little bit better way to do it.
Okay.
But does that make sense?
Okay.
The follow-up for this. Well, let's just make sure we answered the question before we move on. Did we answer the question?
Yeah.
What was the question?
the angular speed of the wheel sprocket.
Find the angular speed of the 2-inch wheel sprocket. What did we end up with here? There it is. Okay, so now we're ready to move on. Here's part B. Well, what do you think I'm going to ask?
Speed of the bike is moving.
Yeah, find the speed of the bike. Find. No, if she's only pedaling 40 RPM, it's not going to be very fast. Find the speed of the bike. Find the linear speed. Find the speed of the bike. Huh. We know omega of what? Okay. Omega for the wheel sprocket is 160 pi radians per minute. Now, let me go back up to the picture here for a second. What does the wheel sprocket here have to do with the larger bike wheel itself? What's the same about them? Why?
Yeah, they're connected. Now this is assuming there's no slipping that's going on, but this wheel is connected to this larger wheel. So whenever this turns, that turns, and it has the same angular speed.
This is omega for the bike wheel. Why in the world would we want to know omega for the larger bike wheel?
Okay. Now, some students get confused about this. The linear speed versus angular speed. Let's go over that one more time. Linear speed versus angular speed. Angular speed is how many radians per minute or per second something is turning. Now, linear speed is how quickly something is moving along the outer edge of the circle. Does that make sense? So if we chose one, like if we took a white marker and put a point somewhere on the edge of that circle and just watch that point go around and around, that's a linear speed. How fast is it moving around the circle? What does that have to do with how fast something's moving on the road? You know what I mean? Yeah, assuming that this bike's not peeling out, that however fast that point is moving around the edge of the circle is exactly equal to how fast the bike is moving forward. That's the relationship here.
So how do we figure this out? What's the formula? We know the formula. It's on here somewhere. V equals R times omega. Yeah. So V is equal to R times omega. So V is equal to the radius, which is 13 inches, times 160 pi radians per minute. And unless it specifically says otherwise, what's the convention here in America for speed? Miles per hour. So that's how you are expected to represent your answers if it's a linear speed. Yeah.
I'm a little confused. So it's 13 inches, but what about the 2-inch sprocket on the bottom? So is that 13 inches from the top to the very center?
From the center. Yeah, from the center of that out is the radius.
Okay.
Does that answer your question?
Yeah.
All right, calculator time. 13 times 160 is 2,080. So it's 2,080 pi. But we got the same problem here again. It's in inches per minute. So I think this is the same conversion that we did a second ago. So let's do the inches first. 1 foot is 12 inches. And then 1 mile is 5,200. Where'd you go? 5,280 feet. So feet are gone, and inches are gone. And then we have 60 minutes is 1 hour. So now minutes are gone. I hope this bike's going faster than 9 miles per hour. That's just pathetic. So 2,080 divided by 12 divided by 5,280 times 60. Oh, this is going to be even slower. This is like a little kid. Multiply it now by pi.
You gotta multiply it.
That's what I do. No, I'm way off. All right. We need that times pi. There we go. 6.187. Let's go 6.2. That must be a little kid. 6.2 miles per hour. They're moseying along. Those are the types of questions you can expect from 6.1 involving linear speed and angular speed. Kind of fun, huh? Right?
Yep.
Yeah.